In this video, we'll be looking at some examples of sequences. Whoa, maybe I can't use that here. Oh, goodness gracious. It's one of my favorite lasers, but it's a bit much in this environment. Here we go. So a sequence, one way to think about it is a list of terms, an ordered list. All right. So here is a formula. A sub n is minus 1 to the n plus 1 over n squared plus 1. And I'll list the first 5 terms. You plug in n equals to 1, n equals to 2, n equals to 3, n equals to 4, n equals to 5. Gives us respectively, plus a half, minus a fifth, plus a tenth, minus a 17th, plus a 1/26th, plus a 26th. So that's an example of a sequence. Here's another one. Sometimes we define a sequence by a formula. Sometimes we can define it recursively. That's what I do here. So here we have a1 is 6, and then the rule is that the n plus 1th term in the sequence is given by 5 times the nth term minus 3. And so we, having the first one, we can calculate the next, and then the next. So 5a1 minus 3 would be 27, and then a3 would be 5a2 minus 3, which would be 132, and then we get 657. Alright, and so forth. So not having an explicit formula for a sub n does not stop us from making meaningful analysis, right? You can kind of see that this limit, that this sequence is going to get bigger and bigger and bigger and bigger. You can already kind of start to see that, right? Next example, a sub n is n over n factorial. So this is n factorial. And that is defined to be 0. 0 factorial is defined to be 1. 1 factorial is defined to be 1. And then n factorial, for n larger than or equal to 2, greater than or equal to 2, is defined to be n times n minus 1 factorial. All right. So like, for example, 2 factorial is 2 times 1 factorial, which is 2. 3 factorial is 3 times 2. Generally speaking, we can think of n factorial as n times n minus 1 times 4 times 3 times 2 times 1. Although, of course, you can leave off the times 1 at the end if you want, but factorial is something we'll be seeing again and again throughout the semester, so you should learn this and this and that. Maybe it'd be a good exercise to calculate n factorial out to like 10 or something, just to kind of familiarize yourself with how factorial works. Anyway, we'll keep coming back to it. Oh, there's the first few. 2 factorial is 2, 3 factorial is 6, 4 factorial is 24, 5 factorial is 120, 6 factorial is 700, what is it? 720, what is it? 8 factorial is 5040, I don't know, I forget, but anyway. So here's n over n factorial, which is giving me 0, then 1 over 1, which is 1, 2 over 2, which is 1, 3 over 6, which is a half, and so forth. Alright, so actually you can start to see what this is. Past 1, it's like 1, 1, 1 over 2, 1 over 6, right? And I'm not sure if I did it or not, but you can in fact simplify that this a sub n, n over n factorial, actually, we can rewrite the formula there as 0 when n equals to 0, and 1 over n minus 1 factorial for n greater than or equal to 1. That makes sense if you just look at the algebra here. If we plug in n factorial as n times n minus 1 factorial, then this n would cancel with that n and just leave us 1 over n minus 1 factorial. But anyway, we'll have lots of opportunities for learning more about the algebra of factorial, so let me go on here. So n factorial, just a little bit more about n factorial here. N factorial, which is n times n minus 1 times n minus 2 times 3 times 2 times 1. This is, in some sense, a formula for it, right? I defined it recursively in the last page. This describes the factorial. In view of example 3, I could do it with algebra instead of pattern matching, so here it is. Well, let's see here, what am I doing? Oh, okay, I looked at it a different way. So this is n over n factorial, which is n over n times dot, 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 dot. The n's cancel, we're left with n minus 1 times n minus 2 times 3 times 2 times 1, and you can recognize that that is in fact n minus 1 factorial. So there's yet another way to see that a sub n is that. Now this only makes sense if n is not equal to 0, right? We can't cancel 0 over 0. But as long as n is greater than or equal to 1, we have this algebra. When n equals to 0, we've got 0 over 0 factorial, as I say down here, which is just 0. All right. Let me stop belaboring example 3. Enough about it. What else do I have to say here? It's important to remember 0 factorial is 1 by definition, and that is really only good for n greater than or equal to 1. All right. And the factorial is key to many central results in this course. Here's another one. Not another factorial, but another example. A to the n is cosine pi n. So suppose we look at a0, a1, dot, 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 this sequence. We have cosine 0, cosine pi, cosine 2 pi, cosine 3 pi, cosine 4 pi, and so forth. Cosine 0 is 1, cosine pi is minus 1, cosine 2 pi is 1, cosine 3 pi is minus 1, cosine 4 pi is 1. So you see what's going on. Plus 1, minus 1, plus 1, minus 1, plus 1, minus 1. So in fact, we can write a nice formula for this one. Cosine pi n is just minus 1 to the n. By the way, in contrast, the sine of pi n is equal to 0. Okay, these things we know from our previous work in calculus and trigonometry and so forth, right? Next up, find a formula for a sub n. Now, finding a formula requires, this means for me thinking. So here's my given list. You might wonder where it comes from. It came from the dark recesses of my imagination. That's it. It's not especially interesting, but there it is. 1, minus 4, 9, minus 16, 25, minus 36. See, so it's got that plus, minus, minus thing going on. To get the plus, minus, the alternating signs, we put up minus 1 to the n. Oh, it's supposed to start at n equals to 2, right? So that's like 1 squared. This is like 2 squared, 3 squared, 4 squared, 5 squared, 6 squared. But since it starts at 2, I need something related to 2, something related to 3, something related to 4, something related to 5. If you think about it for a second, you see that that's n minus 1 squared times minus 1 to the n. That's the pattern here. I should say, finding a sub n from a list requires thinking. I cannot tell you a general algorithm, but there are of course problems where you want to see if you can see the pattern. Here's the list of odd integers, odd positive integers: 3, 5, 7, 9, 11. So if you look at it, you go, okay, so that's 2n plus 1. 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 But for n equals to 1, 2, 3, 4, 5, all matches that pattern. All right. All right. So next up, topic is limits. All right, so we have sequences, and one important idea to keep in mind for sequences is the concept of a limit. I should mention the other way to look at sequences, and this is probably something I would certainly say for math majors early on, is a sequence is simply a function from the natural numbers into the set. Now, this definition of sequence will serve you well in many contexts beyond just reals or complexes or whatever. A sequence is just a function from the natural numbers into your set. So for such a function, there's really only one kind of interesting limit, which is the limit as n goes to infinity. It's in good analogy to the kind of continuous limit we thought about before, namely limit as x goes to infinity of f of x, right? So you can think about like asymptotically, where does the function go to if it does? In the same sense, we could think about a sequence as n goes to infinity. Now, I haven't even drawn the graph for a sequence yet. It's kind of, they're not especially exciting. I've never, I don't know, maybe you'll get more out of them, I don't know, but here's a rough picture for a sequence. Here, I'll try to sketch. So here, let me say that this is a bad picture of what I'm trying to graph here is y equals e to the minus x and y equals e minus e to the minus x. All right. So if I did this better, they should go through. This point would be 0, minus 1. This point up here would be 0, 1 if I did it right? And then I could plot a sequence, just for kicks. And because I haven't done it yet, let's see if I can find my, looking for my red. All right, children, what have you done? leave the house here, you know, and they get into my markers. So, I don't know, this is 1, 2, 3, 4, and this is not the scale, obviously. I mean, who knows, but if I was to look at a sub n equal to -1, if I can't make -1 to the n, e to the minus n, right? Then that would like start out up here, then the next one would be down here, and then up here, and then down there, and then up here, and then down there. Did I do that right? I think here, let me fix it. I need to add a 1 to make my picture right. Okay, because I did positive for n equals to 1, which means I had to have a plus here, right? So, dunk, 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 dunk. And then you can go like this, and 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 like this. And these should be spaced out evenly. I'm sorry, guys. Anyway, you can see that these are sort of all tending towards that, you know, their eventual fate is to converge to the axis here, right? As n goes to infinity, we can kind of see what's going to happen. The limit as n goes to infinity of -1 to the n plus 1 e to the minus n is going to be 0. Now we could prove that by like the squeeze theorem, right? As we'll see here. Actually, maybe we won't see that, so let me just add that here to show that that equals to 0 with the squeeze theorem. Pretty simple. We just go, okay, so minus e to the minus n is less than or equal to -1 to the n plus 1 e to the minus n is less than or equal to e to the minus n, right? Because this is either plus or it's minus. It's stuck between this and that. And the limit as n goes to infinity of plus or minus e to the minus n, well, both of these are 0. So when that goes to 0 and that goes to 0, then the squeeze theorem says the thing in between must also go to 0, right? So by squeeze theorem, the limit as n goes to infinity of -1 to the n plus 1 e to the minus n equals 0. All right. So there would be a somewhat complete argument at the level of this course. So I'm going to go on here. So one important idea to keep in mind as we study limits of sequences is basically that we can interchange the continuous limit we studied before with the limit of a sequence, all right? And this extends to the case, it could be that the limits, we could have something where the limit as x goes to infinity was equal to infinity. You could also have sequences limiting to infinity as n goes to infinity, right? Or you could have this doesn't exist, you could have that doesn't exist. But the larger point here is if we have a function that matches the sequence, then we get the connection between the sequence and the function. I think I'm going to say that as we go on here. All right. You can use L'Hopital's rule. If there exists an appropriate continuous function f which extends a sub n via the rule f of n equals a to the n. All right, so technically speaking, I shouldn't really do calculus on f of n directly because n is not a continuous variable, it's discrete, right? It's hopping from 1 to 2 to 3 to 4 to 5. Now x is a continuous variable, right? So there I can do calculus, I can do L'Hopital's rule, and so forth. So the idea is to replace the sequence with a function which matches at whole numbers, but otherwise is some sort of continuous extension. And then we can use calculus on the extension. All right, so let me show you some examples of what on earth I'm talking about. Example 7 here. Limit as n goes to n e to the minus n. So as n goes to infinity, that goes to infinity, that goes to 0. So that's indeterminate form, right? Infinity times 0 is an indeterminate form. I can rewrite that as n over e to the n. And then, like I said over here, extending n continuously, we can apply the L'Hopital's rule next. So differentiating top and bottom gets me that. And then this clearly goes to 0. That's no longer an indeterminate form, it's just a 1 over something that goes to infinity. So 1 over something that goes to infinity tends to 0. All right. Now, technically speaking, I shouldn't apply L'Hopital's rule to a discrete variable, so my excuse is writing this over here, which is a shorthand for saying replace this function with a function of x, differentiate it, and then go back to this limit again. But rather than writing those 3 extra lines, I'm just going to write this, if that's okay with you guys. All right. Now, so the notation, let me just to belabor it a little bit more here. The notation above is equivalent to writing f of x equals x e to the minus x, then noting that the limit of f of x is the limit of x over e to the x, which by L'Hopital's rule, the honest to goodness L'Hopital's rule for continuous functions, or I should say differentiable functions, is that which then equals to 0, and then by the theorem that connects the limit of the sequence to the limit of the function which matches the sequence at whole numbers, we get that this limit's equal to that limit, which is equal to 0, right? So we could write all of this every time we run into something like this, or we could just write off to the side, extending n continuously, apply L'Hopital's rule next. All right? I prefer to say this sentence as opposed to writing this paragraph. But you do need to say something. If you're going to use a method of calculus on a discrete variable, at least some comment is deserved, okay? All right. Here's another example. To calculate the limit n squared plus 4n plus 6 over n e to the over n e to the n, we've got infinity over infinity is the form here, which is indeterminate. Extending n continuously, I differentiate the top and differentiate the bottom using L'Hopital's rule on the continuous extension of the sequence, right? And then what happens is I can apply L'Hopital's rule again because I've still got infinity over infinity type. When I apply L'Hopital's rule again, I get 2 upstairs and I get this downstairs. Now that goes to infinity, and that's just 2, so infinity wins in the sense that 2 over something very, very large limits to 0. All right? So a couple examples to get us started. So the first order of business here is to figure out how to calculate sequences. And what I'm really telling you here is that the way we calculate limits of sequences is just like how we calculated limits of functions at infinity before. So here I've got 1 plus 10 to the n times minus 3 to the 2n, which I have somehow... Well, this is interesting. How did that be? This is not right, folks. So when I wrote this, I was meaning to put a rather important... Let me fix it. There should be a minus right here, right? There's supposed to be a minus. With that minus to the minus 3 to the minus 2n, then when I rewrite it in the denominator, then it becomes a positive 2n like that. Okay, that's what I meant to write there. Otherwise, the example, without that minus, this thing just blows up. All right, it just diverges clearly from the start. Now with that, I've got something interesting to analyze. So doing the squaring first, minus 3 squared is 9, so we've got 10 over 9, like so. Then I can regroup that as to 10/9 to the n power. And, okay, so it still blows up, but at least it was more interesting the way it blew up. We have 10/9, which as n goes to infinity, goes to infinity, right? Any number larger than 1, if you take the limit as n goes to infinity, it blows up. So that's infinity, example 9 there. All right, yet another example. If you don't have a lot of experience calculating limits at infinity, you need to do more of these, right? Depending on how your Calculus 1 went, you may or may not have actually covered L'Hopital's rule before. If you haven't covered L'Hopital's rule before, then you need to look at it, all right? 2 to the n plus 3 to the n over 4 to the n. So by algebra, we have 2 to the n over 4 to the n and 3 to the n over 4 to the n, which I can simplify as 1/2, or 1 over 2 to the n, I should say, and this is 3/4 to the n. That goes to, this goes to 0, and this goes to 0, so we get 0 plus 0 when the limit's 0. There you go. Now, there's a more careful way of doing limits in terms of epsilons and n's and so forth, and I probably should add a video to talk about that, since we want to have the online calculus equivalent to the residential calculus. And certainly in the residential calculus at the moment, some instructors are still very much talking about epsilons and n's, and as such, I probably owe you some discussion of that. But I don't believe I have it in these notes. I don't think they're in here. I think in these notes I've I have neglected discussion of the careful definition of limit, and I probably should add a video to talk about that. So let's continue on anyway with careless calculation, if you will. Okay, it's not that careless, but here we go. Theorem, every bounded monotonic sequence is convergent. All right, so that's a theorem that we know from real analysis. And what does that mean? What is a bounded monotonic sequence? Bounded means that the sequence, you can find a number below it and above it, which the sequence does not escape. All right. Monotonic means that it's either increasing or decreasing. All right. So if you have a function, if you have a sequence which is either decreasing or increasing, and it's got a couple of values above and below it which it cannot escape, then it follows it's convergent. So here's some examples of that. In fact, this particular one is how do you prove that? I just used this result that r to the n limits to 0 if r is between this and that. All right, so here's a little bit of how that goes. 0 is less than r to the n is less than 1. This inequality right here shows you that this sequence, right, is bounded below by 0, above by 1. And since it's simple enough to show that this is actually a monotonic sequence in the sense that it's, let's see here, I believe it's decreasing, right? Because if you take r 0 less than r less than 1, what happens if you, here, let me just do that calculation. I think I've neglected to put that in here because when I was writing these examples, oh, I'm an idiot. If I just remember what I wrote here, stop covering it up. So here's the proof it's decreasing. A sub n plus 1 is that, which is that, which is that, so we've showed that a sub n plus 1 is less than a sub n, which shows you that the sequence is decreasing, which means it's monotonic, it's bounded, it's monotonic. It follows that, in fact, the more careful and complete statement of this theorem is that every bounded monotonic sequence is convergent. If it's a decreasing sequence, it converges to its greatest lower bound. If it's an increasing sequence, it's converging to its least upper bound, I believe. So in this case, the fact that 0 is the greatest lower bound is, that's why this thing converges to 0. All right. Anyway, and more generally, just fun fact for you as we go on in here. If we're faced with a limit of a constant to the n power, it's either 0 if the absolute value of r is less than 1. It's 1 if r is equal to 1. It does not exist if r is less than minus 1. And it's infinity if r is greater than 1. Let's see here. Next up, we consider a sub n, which is 1 minus n over 2 plus n. Again, I look at the continuous extension of it, because this one, to decide whether or not this is increasing or decreasing, I found it useful to look at calculus. So if I look at the corresponding function, differentiate, I can easily see that that derivative is negative because its formula works out to this, right? So if the derivative is negative, that means that the function is decreasing for x greater than or equal to 1. And so that means that the corresponding sequence is likewise decreasing. Furthermore, we can simplify a sub n by doing this, right? And so what I did there was just to make, this is the same degree numerator and denominator, so that means I can pull out a constant and sort of reduce it to a proper fraction and a number like I do here. And then it's easy enough to see what happens, right? As n goes to infinity, this piece dies, and you're left with minus 1. So the limit as n goes to infinity of a sub n is minus 1. Now, you probably could have done that without using the monotonic sequence theorem here. But it is the case that this sequence is decreasing, that the greatest lower bound is in fact minus 1, right? And by the way, this is in good agreement with the bounded monotonic sequence theorem. Notice that a decreasing sequence is bounded above by its first term, right? Because if it's decreasing, sorry, let me scroll up a bit here. If it's decreasing, then a1 is less than or equal to a2 is less than or equal to a3. So like the first term in the sequence serves as a bound, an upper bound, and On the other hand, no matter how large n gets, this is always a little bit bigger than -1, right? So -1 is the greatest lower bound in this case. And it's also the limit as n goes to infinity. So the point of example 12 is not simply to calculate the limit as n goes to infinity of 1 minus n over 2 plus n. Rather, the point is to illustrate the ideas and concepts present in the bounded monotonic sequence theorem. By the way, as I just mentioned, -1 is the greatest lower bound for a sub n. So I hope this gets you started. I think this is really not a very good substitute for a proper lecture about sequences. Really, a proper calculus course, you should listen to some instructor talk about these things for a couple hours to really absorb these ideas and really think about them more deeply. You probably don't have time for that right now, so this is what I'm trying to do as a substitute for that. I don't know how well this works for you. Certainly you should read your textbook about sequences to try to get some better ideas about what they are. They don't have to be complicated, but they are a little bit different. Now what we're about to do, series, I think it sort of scaffolds above what we're currently doing. So you do need to get an idea of what a sequence, what the limit of a sequence is down well before you go on. And like I said, I'll try to post another video about the careful definition of limit of a sequence just to try to add something a little bit more depth here. Thanks, guys.